Why do some places on Earth behave as if they belong to another world? Why are there depths where familiar rules collapse, where pressure crushes steel as if it were paper? And what does it mean when instruments return signals that no known system can fully explain? These questions sound bold, but they arise from a simple reality. The Mariana Trench, nearly 11 kilometers deep, is the most extreme environment on the planet. Down there, darkness is absolute, temperatures fall close to freezing, and the weight of the ocean becomes almost unimaginable. It is a place where ordinary expectations fail, and where every new measurement forces scientists to reconsider what they thought they understood. But what exactly has been detected at the very bottom, and why do so many findings resist quick explanations? Could these anomalies point to geological processes we have not modeled, or something entirely different? The search for answers begins in the tension between what we know and what still refuses to fit. The deeper the investigation goes, the sharper the questions become. And each of them hints at a wider story waiting to unfold. In the coming exploration, several threads converge into a larger picture that is still taking shape. The trench will be examined not as a single mystery, but as a system where geology, biology, and unexplained signals intersect in unexpected ways. There are seismic tremors that behave differently from typical tectonic patterns, chemical signatures that appear only under pressures found at impossible depths, and recordings that capture sounds with no clear source. Each detail suggests that the bottom of the trench may hold processes that challenge long-standing assumptions about Earth's interior. Attention will shift between the known structure of the oceanic crust, the strange life forms adapted to extreme pressures, and the anomalies that modern research vessels have detected in recent years. Some findings seem to complement one another, while others sharply contradict established models. Understanding how these pieces relate requires looking at the trench not as an isolated geological scar, but as a dynamic environment with multiple overlapping forces. As the narrative unfolds, patterns begin to form, patterns that raise as many questions as they answer. The clues do not point in a single direction, yet together they outline a landscape far more complex than expected. It becomes clear that simple explanations will not suffice, and that the investigation must move deeper into evidence that remains only partially understood. At first glance, the forces inside the Mariana Trench can be compared to a massive, slow-moving hydraulic press. Most people imagine pressure as something abstract, yet here it behaves like a physical weight stacking endlessly on itself. If a human hand were placed at this depth, the force bearing down on every square inch would equal the weight of a fully loaded truck. This everyday comparison helps reveal the true scale of the environment, long before scientific terminology enters the picture. In precise terms, this pressure is the result of hydrostatic load, a phenomenon in which the weight of thousands of meters of seawater compresses everything beneath it. The ocean floor here is shaped by the subduction of the Pacific Plate under the Philippine Plate, creating a geological fold so deep that material from Earth's upper mantle is exposed to near-surface conditions. This is not just a trench. It is an intersection of tectonic motion, mineral transformation, and heat flow that forms a natural laboratory unlike any other. These conditions influence chemical reactions in ways rarely seen elsewhere. Water trapped in descending rock is forced into minerals under enormous pressure, triggering metamorphic changes that release hydrogen, methane, and other gases. Some of these reactions have been proposed as potential analogs for early Earth environments, while others raise debates about whether modern ecosystems could rely on similar energy sources. Such discussions often spark questions in comment sections. Could this be evidence of life forming independently in extreme environments? Or are these signatures simply byproducts of deep Earth chemistry with no biological implication at all? The trench also distorts sound in unusual ways. Acoustic waves bend and scatter under pressure, creating echoes that appear to originate from moving objects, even when nothing solid is present. Oceanographers describe this as refraction in a high-density medium, a mechanism that makes it difficult to trace the source of recorded noises. This has led to speculation about unidentified creatures or mechanical signals, though most interpretations remain grounded in complex physics. Still, the ambiguity fuels ongoing debate about what instruments are truly detecting. Each of these mechanisms, pressure, plate movement, mineral reactions, and acoustic distortion, operates simultaneously. They create a setting where straightforward explanations rarely survive first contact with the data. What else might be acting in such an environment? Several observations from the deepest expeditions form the foundation of what is currently known about the trench. The first involves temperature anomalies recorded just above the sediment layer. Probes routinely measure slight but consistent pulses of heat rising from fissures, far warmer than expected for an area so distant from volcanic zones. This suggests active chemical reactions or hidden geothermal channels that challenge older maps of the subduction interface. A second observation concerns the mineral fragments retrieved by remotely operated vehicles. Some samples contain high-pressure crystal forms usually associated with conditions far deeper within Earth's mantle. Their presence at the seafloor indicates that pieces of descending crust are being compressed and transformed more rapidly than models predict. It also raises the question of how much unseen material is cycling between the surface and the interior. A third point comes from low-frequency acoustic recordings captured over several months. Hydrophones detected rhythmic echoes that shift in tone and amplitude as if moving through layers of different density. Scientists interpret these signals as interactions between seismic tremors and trapped pockets of gas, though the precise pattern remains unresolved. The recordings offer rare clues about processes unfolding in darkness where direct observation is impossible. A fourth element lies in biological evidence. Organisms collected near the Challenger Deep display biochemical adaptations that push the limits of what is considered viable life. Some species contain enzymes that function under pressures capable of crushing most known proteins. Their survival hints at evolutionary pathways shaped entirely by physical extremes, and at metabolisms dependent on chemical sources unavailable in shallower waters. A fifth observation involves sediment distribution across the trench floor. Instead of settling evenly, material forms intricate ridges and depressions that shift subtly over time. These movements imply ongoing micro-landslides or pressure-driven flows that remodel the landscape in slow but persistent cycles. Such changes complicate long-term measurements and introduce uncertainty into every new dataset. Taken together, these observations outline a setting shaped by forces that operate beyond everyday intuition. One interpretation suggests that the unusual heat pulses, acoustic distortions, and mineral transformations arise solely from deep Earth geology. In this view, every anomaly reflects the immense pressure and friction generated as one tectonic plate sinks beneath another. Hydrated minerals release trapped fluids, gases migrate upward through microfractures, and sound waves bend unpredictably in a dense medium. This model works well for many measurements, especially those that align with known subduction zone behavior. Another explanation proposes that chemical systems at extreme depth may operate in ways not yet fully characterized. Some researchers argue that the hydrogen and methane signatures could indicate unconventional reactions occurring between supercompressed water and descending rock. These processes might produce acoustic vibrations that mimic biological or mechanical sources. The strength of this interpretation lies in its grounding in mineral physics and high-pressure chemistry, though it leaves open questions about consistency across different sampling missions. A third model considers biological activity as a contributing factor. Microbes adapted to crushing pressures could theoretically generate gases or chemical traces that resemble abiotic reactions. However, the deep trench remains inhospitable to complex ecosystems, and most evidence for biological influence is sparse and indirect. Therefore, this explanation is often treated as supplementary rather than central. The null hypothesis, used as a baseline, assumes that no extraordinary processes are occurring at all. Under this framework, each observation should emerge from established geological mechanisms without invoking new phenomena. It requires demonstrating that every temperature shift, sound distortion, and mineral anomaly can be reproduced through known interactions of pressure, heat, and plate motion. While this approach provides a disciplined guardrail against speculation, it struggles when datasets contain patterns that do not fit neatly into existing models. Evaluating these possibilities reveals that no single explanation accounts for all observations with equal strength. Some mechanisms match current data closely, while others leave unresolved gaps that invite further investigation. The balance between these interpretations continues to shape how researchers approach the trench. Significant gaps remain in understanding what occurs at the greatest depths of the trench. One of the largest uncertainties involves real-time processes beneath the sediment layer. Sensors offer only brief snapshots, leaving long intervals during which temperature shifts, gas releases, or micro-seismic movements go unrecorded. Without continuous monitoring, many patterns may remain hidden or misinterpreted. Another limitation arises from the technical constraints of deep-sea instrumentation. Cameras distort under intense pressure, hydrophones struggle to isolate overlapping sound waves, and sampling arms can retrieve only tiny fragments of the surrounding rock. Each tool provides partial information, but none can fully capture the complexity of an environment shaped by billions of tons of water and constant tectonic motion. This incomplete picture makes it difficult to confirm whether certain anomalies are routine or exceptional. Uncertainties also extend to chemical signatures found in the trench. While gases like hydrogen and methane have been detected, their source is still unclear. Are they produced by reactions in the subducting crust, or do they arise from deeper mantle processes that rarely reach the seafloor? The inability to trace these compounds back to their exact origin limits attempts to model the full system. Biological questions add further ambiguity. Extreme pressure organisms demonstrate remarkable adaptations, Yet little is known about how their metabolisms interact with surrounding chemistry. Do they influence mineral reactions in measurable ways? Or do they simply endure conditions shaped entirely by geology? The distinction matters, but the data needed to answer it remains sparse. Even seismic interpretations face unresolved tension. Some tremor patterns appear inconsistent with normal plate movement, but without broader coverage it is impossible to determine whether they represent rare events or recurring cycles. The absence of long-term baselines makes it hard to distinguish anomaly from noise. These uncertainties highlight how much of this environment remains beyond current measurement and theory. They also point toward the possibility that entirely new processes may still wait to be identified. The initial questions return with greater clarity when viewed through the evidence gathered so far. The crushing pressure at 11 kilometers depth does not merely distort materials. It reshapes geological behavior in ways rarely seen elsewhere. This alone explains why familiar rules break down and why sensors often return puzzling results. In regions where the oceanic crust bends into the mantle, heat pulses and mineral transformations become natural outcomes of extreme compression rather than signs of unknown forces. The unusual sounds recorded in the trench also fall into place when acoustic physics is considered. Waves bending through dense, uneven layers of water and gas create echoes that imitate movement. Instead of signaling unidentified creatures or mechanical sources, the data reflect a complex interplay of refraction, trapped vibrations, and slow seismic shifts. What once seemed mysterious becomes understandable once the environment is accounted for. The chemical signatures, including hydrogen and methane, fit into established models as well. They can be traced to reactions triggered when minerals in the subducting plate release fluids under immense pressure. Although these reactions are rare at the surface, they become expected at such depths. Their presence does not indicate anything beyond intense geological activity unfolding at the boundary between two tectonic plates. Even the extreme adaptations found in deep-sea organisms align with the physical demands of their environment. Enzymes built to withstand crushing forces may seem extraordinary, yet they represent life responding to conditions rather than defying them. These species reveal how biology can stretch under pressure, not how it breaks scientific laws. In this context, the anomalies observed at the bottom of the Mariana Trench do not imply a separate world operating under alien principles. Instead, they reflect the known physics of an environment at the absolute limits of Earth's natural conditions. The unknowns remain, but they now take the shape of unanswered scientific questions rather than signs of impossibility. The answers to the opening questions lie in the nature of the trench itself. It is a place where immense pressure, tectonic descent, and chemical transformation intersect, producing outcomes that appear mysterious only when viewed from the surface. What is found at the bottom is not beyond imagination but beyond familiarity. Understanding it requires accepting that the extreme can still be natural. At the deepest point of the ocean, the boundary between the known and the unknown tightens into a narrow thread. The trench shows how a single place on Earth can challenge long-held assumptions without breaking them, reminding us that understanding often grows from tension rather than certainty. It reveals a world shaped not by fantasy, but by physics pushed to its furthest edge, where pressure and darkness combine to create forms of motion, chemistry, and life that remain distant from everyday intuition. There is something profoundly human in the effort to explore these depths. Every instrument lowered into the darkness reflects a quiet belief that knowledge expands when questions are pursued with patience. The trench does not offer simple revelations or dramatic turning points. Instead, it provides a slow accumulation of insights, each one small but meaningful, each one adding texture to the way the planet is understood. This journey into the deep also mirrors a deeper curiosity about our place within a vast and complex world. Human beings have always sought frontiers, not out of conquest but out of an urge to comprehend the systems that sustain life. The ocean's deepest point becomes a reminder that even in an age of advanced technology, there remain environments where mystery endures, encouraging humility rather than fear. It shows that certainty is not a requirement for meaning, and that exploration continues even when answers come gradually. The Mariana Trench stands as both a scientific challenge and a philosophical invitation. It invites reflection on how much of Earth remains uncharted, and how much progress depends on accepting uncertainty as a companion rather than an obstacle. It highlights that knowledge is rarely final, and that the willingness to pursue difficult questions often matters more than the answers themselves. Thank you for taking part in this exploration. If you found this journey valuable, consider subscribing to the channel to follow future investigations into the hidden structures of our world.